All right, so our next speaker is Professor Blair Brettmann, also from Georgia Tech. And she's talking about an application of organic material characterization of XRD, looking at cellulose nano crystal gels. So I'll leave it to you.
Great. Thank you very much. Yeah, so I'm happy to be here and really excited that Dr. Garten set me up so well for this. I wish I had gotten a sneak preview so I could have changed the structure because I could have copied her whole metastability structure, but for pharmaceuticals. So we may have some fun side discussions based on this as I talk through it. But my research really is all in organic materials. I do a lot in polymers. I do a lot in pharmaceuticals. I don't know a lot about hard materials, so I'll be a little bit different than some of the other talks. What we're really motivated by here is some of the main challenges in small molecule drug development. So tablets, as many of you probably have noticed, are the most common and most desired form of drug delivery, right? If you were going to take a medicine, let's please just take a tablet and not have to deal with an injection. Unfortunately, up to 40% of newly discovered drugs fail in development due to their poor water solubility. And so, your stomach is water-based and the rest of your body. And so you need a relatively high water solubility in order to be able to use a drug orally. So a lot of them are in kind of this class 2 and class 4, where they have a low solubility and thus are failing. So some of the ways that you can improve this is through crystal engineering. So the ones that I'm going to talk about less today include things like the crystal size. Having a larger crystal, you have less surface area, and so it's going to dissolve less quickly. Same with the crystal shape, surface area based effect. But then we also have the polymorphic form, right? So an amorphous form is going to be less stable, and so it's going to dissolve more readily. And then you have different polymorphs that may be more stable or less stable. And so they're going to dissolve and have a higher or lower solubility based on that. So there's a lot of drug development and crystal engineering design to try to get a polymorphic form that has a high solubility, but can be stabilized. So the reason why I asked Dr. Garten this question is because in pharmaceuticals, if you give someone a drug and it changes its solubility, that changes its performance. And that can change people's health outcomes. And so it's extremely important in the pharmaceutical field that we design these drugs that have this kind of metastable polymorph, but that it also stays stabilized over time, and that we know of all possible polymorphic forms that might have a lower energy, right? And that it might transition into. So that's kind of motivates some of the work that we're doing. Unfortunately, with crystallization, you can have lots and lots and lots of different factors that affect the solid state form. So Dr. Garten talked a lot about the ones that kind of can impact the metastable forms in her hard materials. For pharmaceutical, these are just some of the ones that are included. So we can have things like your solvent, your degree of supersaturation when you make the solution. The surface of the crystallizing vessel can play a large role, whether you use seed crystals or not. How pure your material is, are there contaminants in there that can lead to nucleation of a different polymorph? Of course, temperature, the rate at which you cool it, if you cool it fast or slow, and many others. And so it's really hard to design these systems, especially at an industrial scale and thinking towards producing these that can give you your desired polymorph. So some of the approaches that are used to obtain these higher solubility, more metastable APIs include heterogeneous crystallization onto a substrate. And so you crystallize your drug molecule onto something, or your drug particle onto something else, and hopefully can design that something else to promote the desired nucleation of the polymorph that you want. Another way you can sometimes create these metastable polymorphs is to do homogeneous crystallization, which means it still crystallizes just in the solution out of kind of random molecules bouncing into each other. But you do this in a confined environment. So it can be confined in pores, and that can limit the orientation of the drug molecules and thus lead to only certain polymorphs forming. So these are two of the main approaches people are using to design metastable polymorphs for pharmaceutical applications. So what we set out to do was to use a platform technology for this with cellulose nanocrystal gels. or 3D cellulose nanocrystal scaffolds. Why we picked this is because with nanocellulose materials, we can have control over the surface chemistry of those particles. So nanocellulose is particulate based and it has a lot of surface hydroxyls. So we can do chemistry on that to change the surface chemistry and have a tunable surface. So we can hopefully kind of lead towards desirable polymorphs. We also, with the gels and with some of these 3D structures, we can have control over the pore size, which then would allow us to use some of these confinement effects. So that was the idea when we started this work. Now, some of the reasons why nanocellulose in particular is that it's, has advantages that it's renewable and biocompatible. It also has a low toxicity. So microcrystalline cellulose is used commonly in pharmaceutical formulations. So many of the tablets you have use it as kind of a binder and a filler. It has a low weight with high strength and stiffness, and then this large surface area for hydroxyls. So nanocellulose has been investigated for biomedical applications, including things for membranes for cell encapsulation, making hydrogel networks with them for drug delivery, and as nucleating agents for other particles. So that's why we picked the nanocellulose systems. So if we want to design these gels as crystallization scaffolds for these metastable polymorphs of drugs, we need to explore the 3D structure of the cellulose gels and how these structures impact that drug crystallization. So how does, whether we have, a large pore, or small pore, or other factors impact the formation of different polymorphs? So there's 3D structures and constructs that we worked with here. We first started by making organogels. So these are going to be kind of more swollen gels where the particles are connected by another molecule, and these are in an organic solvent. Then we looked at aerogels where the solvent has been removed and we have a more rigid structure. And then for a comparison, we looked at films. So I'm going to start by talking about our organogel based work. So to make the organogels, we started by doing tempo oxidation onto the surface of the cellulose particles. So this essentially just takes the hydroxyl groups and makes it a carboxylic acid surface. Then we mixed in octadecyl amine, which is a molecule with a large hydrophobic tail, but with this amine group that can interact with our carboxylic acid groups. And the reason why we picked this is because our drugs are more hydrophobic, hence, they're poorly water soluble. And so the hypothesis is that they would kind of localize, drug molecules would localize into this hydrophobic network here and then do their crystallization. And then we did the physical network formation. The solvent we chose was DMSO because we could disperse cellulose nanoparticles in that relatively well. We did not do water like hydrogels because it's, drugs are not soluble in water. So it would not help us very much. So when we add the drugs to these, we do them after we're adding our octadecyl amine. We dissolve the drug into the DMSO, and then we do the kind of heating and cooling that leads to the network formation. And the first 2 drugs I'm going to talk about are sulfur-based drugs, sulfamerazine and sulfamethoxazole. And I guess we also put sulfapyridine in this. And the first thing we looked at was, okay, we're thinking about these 3D constructs. We make these gels. How are the gels going to behave once the drug particles are there? Well, probably not surprisingly to people who played with gels, if you take a gel and you throw some particles in them, the gel strength is going to, decrease, right? It breaks up that network. So this does tell us that our API is kind of localizing into the gels because it's breaking up their network, but it is leading to not very good gel strength. And so it's a concern we're going to have to think about going forward. Then we, looked into, okay, what form is crystallizing when we do this? So our sulfamethoxazole, when we purchase it from Sigma, Aldrich, or whoever, comes as forms 1 and 4. And when we did this process to precipitate our drug in these gels, we got sulfamethoxazole recovered as an amorphous material. So it wasn't even crystalline in this case. So you can see our XRD, which we're using here to identify which polymorph we have. Our sulfamethoxazole in the gel only has the peaks from cellulose, right? Cellulose is in the gel. We compared that to the as received, as well as to just recrystallization from DMSO with our octadecyl amine and recrystallization from DMSO on its own. Supporting data from our DSC also shows this. So that was with one of the drugs. So clearly we're not, crystallizing what we would without having the 3D construct, and that the cellulose is playing a role. Now for sulfamarazine, we found a little bit different behavior. Instead of having the amorphous form recovered, we get a mixture of different polymorphs. So again, here we have our crystallized from the gel. This is as received from DMSO and from ODA in DMSO. So as received in this case was form 2. And because it was kind of a mess, we compared it to powder patterns in the Cambridge Structural Database. We were able to see that we had a mixture of different forms, definitely form 1 and 2. And the closest other match we can find is this one that doesn't have a normal name, I guess, P210C. So a less common polymorph. And so we're seeing this mixture of polymorph form when we are doing the crystallization in these gels. So this is a little bit concerning, right? We want to create a polymorph that we know what it is. We have a lot of control over it. We are seeing that we have a difference after we crystallize in the gels, but we're getting kind of a mess, right? And this comes down to, as we thought about it more, cellulose itself. So cellulose is extracted from plant matter. And in the extraction process, they remove a lot of things that are not cellulose, but not everything. And so cellulose nanoparticles tend to have other contaminants on them, such as hemicellulose. And so what we came to realize is that some of our issues that we're dealing with are the fact that our cellulose nanocrystal material itself is heterogeneous. And so that leads to different microenvironments for the drug particles and thus different polymorphs forming. The other thing that we think might be contributing is this organogel approach, because we have an inconsistent and a dynamic gel structure. So we don't always get perfect, dispersion of the cellulose in DMSO. This is dynamic. And so these are 2 areas where we decided to move forward and try to investigate further. So I'm going to talk about the heterogeneity problem first, which was the one that we could at least somewhat address very readily. This one was made very obvious when we tested another drug, sulfapyridine, with 3 different sources of nanocellulose. And so we bought nanocellulose from Celluforce. We bought nanocellulose from the Forest Products Lab in Maine. And we obtained a proprietary one from a company that collaborates with the RBI for yet another source of nanocellulose. What we see is that depending on the nanocellulose we use, we see different polymorphs form when we do our crystallization in organogels. So as received, it was form 3. Celluforce, it formed form 3 as well. But when we use Forest Products Lab, we got a mixture, form 3, 4, and 5. When we use this proprietary one, we got a mixture of 2, 3, and 5. And so clearly this shows us that our cellulose source is playing a big role in the precipitation and the polymorph formation. So we decided to evaluate these in more depth. So we have the 3 sources of the cellulose, and then we did 3 different cleaning procedures on them, right? I said there's leftover things from the extraction process. The one was dialysis, trying to remove salts and other contaminants like that might be present. Then we did acetone washing, and then oxalate extraction with ethanol. Both of those should remove kind of more strongly stuck organic materials such as hemicelluloses from the surface. So this is our XRD analysis of the different sources, because potentially also their crystalline form may play a role in which polymorphs are forming. So in this case, all 3 of our sources contain cellulose 1 beta peaks, but our FPL sources contain both cellulose 2 and cellulose 1 beta. And so we even have different crystal forms present for the cellulose itself, depending on which source we're using. And then the main kind of focus for us, because we think we have this organic contamination, is the surface charge. So our FPL cellulose, you can see from the blue points are going to be the ones where I haven't done any cleaning of them. This is as received and dispersed. So you see that both the FPL and the Celluforce are highly negatively charged, right? So we kind of have these colors. Red is in the area where it's highly, yellow it's somewhat, and blue it's barely charged. So you can see that our as received for those are highly negatively charged, whereas our as received of this proprietary one is essentially uncharged. Now, when we do dialysis, which is the green ones, you see that it doesn't change very much, right? They kind of stay in their same zone. And then when we do oxalate extraction for with ethanol and then the acetone wash, we see a significant decrease in the magnitude of the surface charge with for the FPL and the celluphores, right? And then for the CNC3 here, it stays about the same. It was not very charged in the first place. So what that tells us is we're likely removing some sort of contaminant that adds to this negative charge when we do our washing. So oxalate extraction with ethanol and acetone decreases the surface charge. And what we think we're removing is something like xylane, our hemicellulose component there that has some of these negative charges on it as well. So what this does is kind of give us a pathway to have more homogeneous cellulose going forward with our studies. So essentially we decided going forward, we wash with acetone, and we're not going to play around with doing anything, trying to use anything without a wash first. So try to improve our consistency there. So that was the first challenge and concern that we needed to address. Then the second one was the fact that we have this kind of inconsistent and dynamic gel structure that may be making it hard to controllably produce given certain polymorphs. So here, what we're going to do is instead of working with these organogels, we're going to prepare aerogels kind of independently of the drug being there, and then add a drug solution and do the crystallization afterwards. So this gives us a nice preformed scaffold where we have a lot of control while we make it. We have, there's known ways to control the pore sizes in these, and they have a little bit better kind of mechanical properties and consistency. And then we're also going to compare those to drug crystallization in films, which have very little porosity. So in this case, the drug we chose to work with is ROY, which actually is not a drug yet, it's a drug precursor, but it's one of the most fun ones. If you ever, going to do small molecule crystallization studies, this is a good one to pick, because it forms different polymorphs that have different colors. And so it's a little bit easier to, as much as we want to use XRD, when you're working with organic materials, it's expensive because it takes a long time to get a good pattern. So if we can do some initial screening with our lovely colors, this is helpful. So it forms lots of polymorphs, including ones that are red prisms, orange needles, yellow needles, orange plates, and all of that. And so they have these distinct crystals, they have different melting temperatures, Raman spectra, and XRD as well. So this one's a nice kind of model system to work with, lots of data available in the literature. So then we form our cellulose nanomaterial aerogels. We chose the aerogels. I mentioned some of the reasons already, but also CNCs disperse well in water. And so, we can make these out of water and know we had good dispersion in the first place. If we want to use lots of different solvents, we're going to be very limited if we try to do organogels. So with this, we can disperse in water, and then as long as they're stable in the other solvents, we have a lot more solvent flexibility. It also requires less solvent and provides a more rigid scaffold. And then the idea is that the crystallization control, right, being able to control which polymorph occurs, is going to occur via the interaction with these aerogel surfaces and the surface on the kind of surface of the cellulose materials, and then also confinement within the pores, because we do have confinement. And then we compare these to cellulose nanocrystal films. So these we did solvent casting from 1 weight % suspensions. These do not have any distinct pores, and when measured by AFM, we had a surface roughness about 2 to 4 nanometers. So when we do ROY from the films, what we see is the nucleation and formation of multiple different polymorphs. So crystals are on the surface, so we can see those in our SEM images, for example, right here, but then they're also embedded within the films. And with some of our kind of microscopy of the transmission, we could see that as well. And so we're getting some penetration of the drug and crystallization into the films, and then some on the surface. So what this means is that the films are, very influenced by just the bulk crystallization. So the polymorphs, a lot of them that form are the same ones that are forming in our bulk crystallization, with some kind of additional polymorphs forming due to penetration into the films. Now, when we did the crystallization of ROY and aerogels, only the orange needle crystal, So it's a much more consistent system than, scaffold than with the films. So here's all our data. We had our ramen, our DSC, and our XRD all showed that we had the orange needle crystallizing in the films. So what we concluded from a lot of this is that our organogels can provide some polymorph control, but we get a combination of polymorphs crystallized, and it's hard to distinguish some of the bulk solvent considerations. The aerogels provide good control over the polymorphism. I didn't talk about it, but we also did some studies with indomethacin that showed they're really, really well stabilized within these aerogels. It's very hard for them to transition from one polymorph to another because of the kind of steric effects from the other, or from the scaffold. And then we think that hydrogen bonding with the cellulose nanocrystals enables this stabilization. And then films do not provide good polymorph control. We got this combination of different polymorphs form and bulk crystallization was prevalent. So, the question kind of is, where do we go from here? So if we want to design materials so that we can crystallize a given polymorph, we know what polymorph it is. Maybe someday in the future, we can even predict which one's going to form. We want to do more work on understanding the pore size of this, right? We make these aerogels, we've got these nice aerogels. Okay, how do we tune the pore size and what specifically are the pore size effects on them? And then the next step would be doing the surface templating. So all of it done, that I presented with our aerogels so far, just had, the hydroxyl groups from the cellulose nanocrystals. But we could also put the carboxylic acid groups on there. We can add polymers to the surface, all sorts of different surface functional groups that will impact what polymorph forms. But then the other thing is, okay, we had this kind of challenge where we were getting these multiple polymorphs, right? And I mentioned when I was asking Dr. Garten about, is there a drive in these fields to know all the polymorphs, right? And one of the big challenges in pharmaceutics is discovering the polymorphs and making sure you find all of them. So a good example of this is a drug ritonavir, and they put it out on the market in one polymorph form, and forget how many years afterwards, a new polymorph suddenly came into existence that had never been seen during all of the discovery. They think it kind of made its way from lab to lab on people's shoes and contaminated all the batches. And this new polymorph had a lower solubility, and the drug had to be pulled from market. And this was an important drug for HIV patients. So eventually they made an amorphous form that was stabilized, and things are good now. But what it means is it's really important to be able to discover all of them. So one of the things we're looking at with these scaffolds is, can we use this kind of fact that it will stabilize these mixtures of polymorphs, that we can modify the surface and form different polymorphs? Can we use this as a polymorph discovery tool? And potentially, be able to discover polymorphs that have not been, would not be discovered necessarily otherwise. So yeah, just want to finish on some of the challenges and opportunities with using these cellulose nanomaterials with pharmaceuticals. So they have this high surface area, readily tunable surface functional groups, which is really promising for heterogeneous crystallization control. With aerogels, we can make these scaffolds pretty easily, and so that gives us some more control. Overall, we observe really good stability of metastable forms and ability to stabilize multiple forms. So this might be a tool in polymorph screening. But we still have remaining challenges in these heterogeneities from cellulose nanomaterials because they come from natural sources that will need to be addressed if it's used to make kind of drugs for actual production. And the hierarchical nature of these scaffolds, so having some small pores, some medium pores, some large pores, could also contribute to the mixture of polymorphs. So hopefully you guys learned a little bit about pharmaceuticals and this application. This work was all done by my former PhD student, Manali Banerjee, as well as some really great undergrad students, Sarah Spatula and Grace Willows, and sponsored by the Renewable Bioproducts Institute.
We have a couple of minutes. Do you have any questions for Professor Brettmann?
Very nice talk. So you talked a lot about polymorph selection, seeking polymorphs with high solubility and other advantages. And another approach is obviously co-crystallization. What are the pros and cons of approaching different polymorphs versus co-crystal solvent?
Yeah, that's a good question. I had done work in labs that do both and all the different approaches. I think, co-crystallization has its advantages, and I think you have a little more control over like stability with them, but you're also wasting a lot of mass, right? And so from our chemical engineer's perspective, being able to control that, especially if it's a high dose drug, right? Where, you need to have a relatively high amount of the drug in the tablet. So those are ones off the top of my head. But I think my experience with the crystallization folks is we want to try as many things as we can because it's such a big problem. So they also do salts and many other approaches to try to address this because there's just so many challenges with getting there.
Any additional questions?
Why is the ODA, oxydecylamine? So it's an easy to use molecule that would hydrogen bond at one end, but then provide a hydrophobic space for the drug to localize. It also has been used previously to make organogels with cellulose nanomaterials. So we knew that there's a decent likelihood we could get gels out of it.
Any others? Okay. Thank